Hi, we are presenting Shor's algorithm. The algorithm is used to find prime factors of a large number, say m. There are several steps involved in this process. One of it is the problem of period finding, which takes exponential time if done classically. So, the problem of period finding is given a and n, we need to find x such that f of x is 1. For example, say a is 4, n is 7. A simple way to solve this problem is start with 1, multiply with 4 and take mod 7. Then iterate it till we get 1. The number of iterations is x. That is what we are looking for. But the time complexity of this classical approach is of exponential order. So let's rephrase the problem in a quantum way. Let's define a unitary operator u like this and proceed just like we did in classical approach. Look at the last line. We have found an eigenvalue problem. If we define a vector psi s like this, we find that psi s is in general an eigenvector of our unitary operator u, and luckily x is present in the phase of an eigenvalue. There exists a quantum circuit that estimates the phase of eigenvalues of any operator. In our case, it's the operator u. Now let's try to understand its building blocks. Starting with inverse of quantum Fourier transform. Well, inverse QFT is just a way to compute inverse DFT of any given sequence. Let's try to build a quantum circuit out of the standard inverse DFT matrix. Allow us to swap these highlighted rows without stating the reason right now, but we'll come back to it later. We partition the matrix like this and simplify a bit. On careful observation, we find that these partitions can be expressed in terms of these smaller matrices written on the right, like this. And then we factorize like this. The first one is a diagonal matrix. So we can further factorize the first matrix like this. The first matrix seems like H is multiplied to a 4 cross 4 identity matrix. In fact, it is a tensor product of a 4 cross 4 identity matrix and Hadamard matrix denoted with a circled cross symbol. Similarly, there is another tensor product in the last bracket. Tensor products sound a bit complicated, but it is very simple quantum circuit implementation. Two separated operations done on separate qubits can be written as a single operation equal to tensor product of the individual operations done on the tensor product of the qubits. Thus, we get simple circuits for the two tensor products present here. Now, focusing on the middle two matrices mapped to controlled gate operations as shown in the middle circuits, the bottommost line in these circuits are for least significant bit, which flip more frequently. The top line for the most significant bit, which flip less frequently. On an intuitive level, the transition from I to R3 is less frequent in the matrix. So, R3 should be applied to the topmost qubit, and similarly R2 should be applied to the middle qubit. Now, we can arrange these blocks in correct order, like this, and like this, and like this. We can now simplify f2 prime as well. Following the same approach as earlier, we can now draw complete f3 prime circuit using these basic gates. Now let's come back to the swapping that we did in the beginning. Actually, in this circuit, the most significant bit of the output comes at the bottom line. So we need to flip the order to be consistent with the convention throughout the circuit, like this. We just saw how we can derive QFT circuit from the standard DFT matrix. Now let's figure out how to realize the unitary operation U we started with. For this operation, we can write a truth table like this. And we should be concerned only with these cases because the other two cases are trivial. If we swap x2 and x3, then swap x1 and x2, we get the desired y1 y2 and y3. The swapping of qubits is possible using swap gates as shown in the circuit. Here we summarize how to obtain quantum circuit modular operations. So, at this point of time, you might have understood all the building blocks of the quantum phase estimation. Now, let us try to understand how these blocks work together. We have two quantum registers, one loaded with ket zeros, other loaded with eigenvector of our operator u. Using the series of controlled u operations, we can modify ket zero vectors to encode phase operations in them. Mathematically, the expression looks like this. Then we can take inverse Fourier transform of this quantum state and measure to get phase information that contains answer to the period finding problem. Thank you. So we see that by using this quantum circuit, we are able to solve a problem which would take a lot of time and resources. Due to exponential runtime scaling using classical algorithm, we are able to solve for n with nearly 230 digits, which took nearly 2000 CPU years. In contrast, Shor's factoring algorithm has polynomial runtime scaling, so it is possible to perform same calculations in a matter of minutes. Thank you.